then hand things over to Steve. Right, and one of them being the notifications and some sounds. So I don't want you to get some disruptions when you're listening to the session. So if you can just ensure that you follow the instructions here on how to untick or enable those sounds and notifications. Right, and then some of the common questions, a lot of people always ask about the slides and the recording certificate of attendance. Yes, we will be providing you with a copy of the slides and the recording. So just always ensure that you check your emails in the next 2 business days. Just also check under junk or spam folder, because sometimes tend to not go into the inbox. We will be providing you with the certificate of attendance. However, you need to stay with us up until the end of the session. So I'll be sharing the QR code on or the link that you need to follow in order to claim the certificate of attendance. So at the end, after Q&A, I will provide you with the information on how to claim your certificate of attendance. Once again, for those who are joining us, welcome. My name is Perry Dikotla. I'm based in the South African office, and I just thought I'll give you just an overview of what we do here at EIT. So when you think of EIT, think engineering. So we specialize in engineering, focus on delivering engineering programs. You'll see that on the slides that our courses starts from professional certificates. We have diplomas, advanced diplomas, undergraduate, graduate certificates. We have bachelor's, master's, all the way to Doctor of Engineering. We're offering industry-aligned programs, which means what you learn at EIT, it's what will still be relevant in the industry. And we also, just like any higher education provider or university in Australia, we are accredited with the Australian government, TEXA. We are also having some of our programs that recognized under 3 international engineering accords. Just to give our students a global engineering perspective, we source our lecturers or instructors from different parts of the globe. And we also give our students an opportunity to sort of like interact with engineers from all over the globe. We use a very unique methods in terms of delivering our programs. We have live interactive webinars that you can go through. We have remote labs, some simulations in terms of how we deliver our practicals. All this information, it's on our website, so you can always just read more on that. And yeah, so one of the reason, some of the reason, there are so many reasons why people choose to study with us. What always stands out for me is the quality of education that we provide. A lot of students always mention that, but there's a whole lot of more. And as I've mentioned, that there's a lot that you can get from our website in terms of successful stories from our students from all over the globe, just sharing the experience or their experience of learning at EIT. And while we're still on that, we've got like a couple of awards, and I believe this is just a reflection of our commitment to our students and communities at large. So once again, welcome to our 6 pieces of physics as applied to engineering. This will be presented by our Dean, Dr. Steve Mackay. So feel free to make use of comment section. Feel free to share your comments or some of the feedback. So for now, I will then hand things over to Steve. Thanks.
Thanks very much, Barry, and really great to see everyone here. Thanks, Britta, for orchestrating this as well. And thank you, your wonderful people out there. I'm very excited to do this 45-minute, 50-minute presentation with, guess what, 100 slides. It's actually quite unbelievable, Carolina, 100 slides. So I just want to quickly take control, and I'll just quickly take control. So I've got... my scribbles ready. Yep, I can scribble on stuff. And it really is going to be mostly by me, although I'm going to be using Python to assist. And we will make sure that you get all the slides. 100 slides means you're not going to cover every word on every slide, unfortunately, but I want to talk about the course in a minute. But this is my background. I've got a very practical and eclectic background, I suppose, and I just love learning. And this presentation has been probably put together by me because I want to learn more about physics, which I'm passionate about. And it's based around to see Richard Feynman, who was a Nobel physicist. And I just dropped out of a meeting with some colleagues and they said, oh, that's the bongo drummer. And he definitely was a very big bongo drummer as well. So a very clever individual. Um, and I've got these topics here, which, as you can see, there's quite a lot of stuff here. A lot of you would be familiar with a lot of the stuff. So atoms in motion, basic physics. So I'm going to be going over a lot of old ground, but hopefully I can bring up some new ground, which is to show you how you can use Python, which is the programming language, to do some of the demonstrations. And this is done literally in a few seconds, these Python programs. And I'm going to show you how. So I'm going to go through basic physics and the other sciences. I know you may say, why on earth are you going to be interested in psychology? Conservation of energy, and a few of the other conservation laws, theory of gravitation, which, as you are aware, is still no one understands where it comes from. But one of the things it does have is a delay. And there's a huge, beautiful course actually from MIT for virtually free on looking at the gravitation waves and analyzing them. And it's very much a live topic. And then I want to spend some time about quantum behavior and perhaps agonize, dare I use the word agonize, over the discrepancy between quantum behavior and classical physics. We need to get them together. And of course, gravitation, quantum mechanics, there's still a little bit of a chasm between them. And I'm definitely not an expert in them. And then some illustrations with Python to take home. I'm going to actually build that into the sessions here. I was testing out with Berry the demonstrations, and they're fairly vanilla demonstrations. But there were some problems with one of them, one of the computers, and but it should all run okay. But if it doesn't, you've got all copies of all the slides and all um, the actual programs. And I will obviously do some sharing later and I'll test it out. So I'm going to share, I'm just going to try sharing now so I can just share and see if it works. Screen, browse. I'm just going to try and see if I can share the Windows screen. Nope, that one there. Nope, not the right one. Python programs, Explorer, file. I just want to make sure I'm getting onto the right Anaconda. Let's see if that comes up there. Nope, not the right one. That's the basic program I'll be using. So I'm just going to go back, stop sharing. Let's try again. Sorry, I'm just trying to share this, Barry. Just let me try stand out, side by side reporter, content only, content from camera, Excel, browse my computer. Let's try that one. No, wrong. Just trying to get the sharing right. Windows, should it be Windows, Barry?
Yes.
Yeah, so Windows, File Explorer, File Explorer, quantum double slit. Okay, here's something interesting. Let's see what that comes up. Okay, here you are. Can you see that, Barry? The
Yes.
double slit experiment? Okay.
Yes.
I think we should be okay then. I will obviously go back again and make sure that the sharing. So I'll just go back. You lobby. It's all a bit you
Do you want me?
lobby.
Do you want me to share the slides, Steve?
Yeah, if you could, I'm just going to quickly close that down. Do I need to stop sharing? Let me just go back. Okay. Step. Okay. Thanks very much. Okay, so hopefully you all saw that first little introduction to the slides. We're going to have to jump around a bit with the slides, but Barry's hopefully across that. Sorry about that extra work, Barry, but hopefully it all plays out. And here we go. Okay, so as I said, when I get to the sections, I will try and jump in at the right time. So really what we're going to be doing is looking at a lot of slides, as I said, but don't fear, they will be made copies. You will get copies of them. And as I said, we're going to be looking at quite a few sections, and I'm just going to look at atoms in motion first of all, and then we'll look at introduction to physics. So really, it's all about physics being a vast field, and hopefully I can give you some views on the various scientific laws. So, for example, you have Newton's laws, you have Einstein's discoveries, and every law is basically an approximation. Nothing's precise. So the idea is that we're going to be, looking at the laws as an approximation, and then we actually create a hypothesis, and then we have what we call evolving understanding. So we gradually get to know what's going on as life moves on. So things, for example, you all will clearly remember Newton's laws: force equals mass times acceleration. Nothing could be more cast in concrete than that. And now, of course, we say, no, that's not quite true anymore. We actually have Einstein coming along saying, no, 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 no. When you move very fast, your mass actually increases. So, those sort of things mean that we interpret the law slightly differently as time goes on. And then that's why we have this bit of a chasm at the moment between classical physics and quantum mechanics and theory of relativity. There's a very few sort of gaps which have been developed. And obviously the idea with physicists today is to try and unify it all into the grand unified theory, which of course is still a little bit elusive. But I'm sure there's some of you out there will say, no, that's not elusive. So the first thing is, let's talk about atomic motion and states of matter. And I also want to just tell you a little bit about the preparation of this course. I prepared this course. I know you'll be a bit shocked to hear this. I prepared this course in about 2 hours. So all 100 slides, all the programs, about 2 hours work. You may say that sounds bizarre, but I used AI. The only problem with AI is that it's created all the slides. I had to go through it, and of course, I then had to do a critique of it because it wasn't quite right. And if you look at the slides, I'll be most grateful when you look at the slides, see if you can find any errors. And certainly in the text, I'm pretty sure the text is pretty good, because what I did is I scanned all the pages in from the book, and I then said, okay, I want to create PowerPoint slides. So I did that, as I said, all in about 2 hours. Very impressive. But of course, some of the scans were misinterpreted and some issues there. So there was a bit of a issue to try and actually pick up the errors. And there are some errors in the stuff, which I will point out to you. But where I fell down a little bit was the graphics. The graphics are some very good graphics, very clever graphics, nice pictures, but some of them are a little bit strange. But as I said, you will be able to identify them, and hopefully you'll text them in the box there, and we can all talk about them and have a little chat. So first thing is, atoms are in perpetual motion, and everything is based around that. And as I said, we have things such as molecular motion, and that's basically the building block. And we have compression effects, temperature influences, density effects. And in fact, I'm doing a great course at the moment on thermodynamics, which is obviously to deal with matter and issues with entropy and stuff like that. So we've got solids, liquids, gases, and obviously one of the interesting things I always find fascinating is helium is never freezes. Quite amazing. And of course, we have various structures here with ice. And we have evaporation and condensation. And of course, blowing air over a liquid reduces the condensation by removing the water molecules. So why does that happen? Well, it's a pretty well studied phenomenon. But basically, as you remove the water molecules, which are gas, over the liquid, you move them away. Hello, there's a space there. Therefore, you create more evaporation. So it's a little bit more complicated than ChatGPT's put in my little slide there, but it's on the right track. And then, of course, condensation. And there's quite a few interesting things there with condensation. Equilibrium is a very important process, and that's very related to thermodynamics. Equilibrium is a pretty good topic to talk about. Now, I'm going to try, whether I get this right or not, Barry, I'm going to try, just to remember which slide I'm on at the moment. I'm going to try and share the demo on the gas. I'm just going to try and do that. Can you see that, Barry? Can you see atomic motion and pressure at the top?
Yes, it's now in.
Excellent. Thank you. Okay, so this is a program. This is a program, guys and girls, ladies and gentlemen. This is a program written by ChatGPT. It's a beautiful Python program. And I went through it. I found a few errors in it, which I had to fix, which took a little bit of time, but quite impressive. I think, Carolina, you'd be impressed, wouldn't you? So here we go. So I'm running it in Notebook, and this is going to show you the gas thing. And this is a great demonstration of atomic motion. And look at that. Gas particle motion in a box. Can you see them, all the particles jumping around? Can you see the particles moving around, Barry, or is it all static?
Yes, we can see them moving around.
Ah, brilliant. Excellent. Thank you very much. That's fantastic. So this is a brilliant little demonstration of atomic motion. Brilliant. Absolutely brilliant. And all created by a little Python program, which you out there should be able to create. And we'll make these available for you. But as I said, a beautiful little program illustrating the basics there. Anyway, let's go back to the slides. Barry, if you could just pull those slides back again. Sorry to give you so much work. If you can pull those slides back again. Brilliant. Excellent. Thanks very much. Sorry about that all the time. We've just got anything. So chemical reactions, we're back on. I think we're back on the chemical reactions. Yep. Brilliant. Yep. Excellent. Yeah. Thanks. Okay. Oh, just jumped off again. Do I stop sharing maybe? No,
it's all good.
Okay, great. Okay, thanks so much, Barry. I'm sorry to work you so hard on this particular presentation, because what we're trying to do is we're trying to jump to the programs which I'm running as well as do the slides. And obviously Teams isn't quite designed for that. But look, it's a good start. So what we've got over here is, let me take control. So we're all on the same page. Thank you very much. Okay, here we go again. So chemical reactions and burning obviously are physical versus chemical changes, carbon burning, and those are all chemical versus physical changes. Molecular structure and chemistry, physics obviously says to you, you can have molecules all stuck together, but the actual pattern in which they are stuck together could determine their characteristics. Again, a really interesting observation. And then, of course, evidence for atoms. In the early days, people said, what are these things called atoms? And there was a Greek called Democritus who actually theorized about atoms about 3,000 years ago. But there was still a debate until, 200 years ago about atoms, whether they exist or not. So they're fairly interesting animals to have around. And we had a thing called Brownian motion, which actually gave us the first indications. And Einstein, by the way, wrote a paper about that about 100 years ago, 110 years ago, about Brownian motion. And that's a really interesting little demonstration, which again, Barry, at the risk of stretching us, I'm going to run a little demonstration with Brownian motion. If I can, let me just go into that. Brownian motion, there we go. We've got Brownian motion. Let's try this again. We're going to go to the Brownian motion demo. And here we go. Brownian motion. There we go. Okay, does everyone see Brownian motion simulation?
Yes.
Okay, so I'm going to run. Do you see that, Barry?
Yes.
Excellent. Okay, thanks. So I'm going to run this program. This is Brownian motion, a little bit ambitious, of course, as we know, always ambitious. So here we go. I'm going to run this so you run each block of cells, and then we have a demonstration of Brownian motion. Can you see there a little atom being nudged around very strangely, and that's Brownian motion, nudged by stuff hidden from us. This is Brownian motion. So the particles moving around, and that's what we got, Brownian motion, all put together by a beautiful little Python program put together by AI, ChatGPT. In a few seconds, obviously I've shown some changes to it because I wasn't very happy with it, but it's quite good. Okay, so Barry, if we can go back again, time is always tight. Sorry about that. If we can go back to the slides. Thanks very much. Stop sharing. Great. Okay, yep. And we move on. Just going to go back to the slide I was at.
Yes.
So everything takes time, unfortunately. So thanks very much. So the Brownian motion is obviously the slide we were looking at, and this is the evidence for atoms. And again, as I said, I gave you a quick demonstration of it. And obviously, the atomic hypothesis is pretty well known. Life is pretty complex, and obviously everything is made up of atoms in various arrangements. And as I said, that actually gives you different characteristics of the atoms when they stuck together in different ways. So let's have a talk about physics and the unified framework. And it's probably, as this guy here, Richard Feynman, said, he said, physics is like a game. It's like a chess game. So you come along, you see someone playing chess, and you say, hey, I wonder what the rules are of that chess game. So you don't know what the game is, you don't know what the rules are, but you as a physicist come along and you observe the chess game and say, I wonder what the rules are. You know, you can move pawn to rook 5 or blah, blah, blah. What are the rules? And that is where it dropped out for some reason.
Yeah.
I don't know why.
Thanks.
So,
Thanks.
if you can that slide, thanks very much. Sorry about it. Very dynamic presentation, everyone. Thank you very much for hanging in there. I'm on a wireless connection, and I dropped out for some reason in Perth. Perth should be pretty up to date, but probably not. If we can just go to that slide, or do you want me to take control, Barry? You're
yes.
okay?
Yeah, you can take control.
Thanks. Okay, so really oh, great, excellent. Okay, so the issues, as I said, is that we've got these magnetism, which, as I was saying, moving charges will current. In other words, you've got current. And the other beautiful thing about if you go into Maxwell's equations, which basically give you a unified view of electromagnetic fields, you actually find that you can actually relate magnetism to electrical fields when you look at relativistic effects as well, but we're not going to go into that now. And understanding atoms and forces, obviously we need to have a pretty good understanding of the atomic structure, electromagnetic forces, and the charge balance. Obviously atoms are usually neutral, apart from things like called ions. And obviously you have the electromagnetic spectrum, which is also, which has a huge range. And again, a fascinating world to be in. In fact, one of the issues which you're all probably aware of is when you go into different media like that, you've got different media, you'll find that the optical media, you'll find there'll be diffraction occurring. And again, it's actually a fascinating area because it's not as you're taught at school or at physics, at first or second year physics, it's a lot more complicated than that. You've got atoms here that actually interact with the wave coming in, and they actually cause the diffraction. But again, a really interesting area. And of course, we've got everything operating at the atomic scale, which I will demonstrate in a tick. So we have this issue now with wave-particle duality, which means that everything is actually can behave as a particle or a wave. And of course, you've got guys like Heisenberg, Schrödinger created an uncertainty principle, which again, I'll come back to. And of course, probabilistic laws are a key part. And Einstein was really annoyed by that. He said, very interesting comment he made, and he said, you know, God doesn't play dice with the universe. So you know, those sort of comments are really interesting to make. But anyway, the uncertainty principle is a really important underlying principle to do with physics and, in fact, with life. And that is that you can't actually predict the location of any particular atom or particle with any certainty. There's always a choice between position and speed. You can't have both. You can't have your cake and eat it. So that's quite important. I just want to put my camera on. I'm sorry, you can't see me. I apologize for that. So this wave-particle unity is something which I wanted to run a demonstration on later, but we'll come back to that in a tick. And of course, we've got nuclei and particles, and obviously, as we talk further about in the book, it's actually quite interesting to see that nuclear energy is probably many, many more times greater than chemical energy. So very important concept. And of course, then you've got strong nuclear force, which is when you've got your protons all stuck together in the middle of your atom. Of course, because they're all positive charges, you'd expect them to push apart. But of course, the nuclear force says, no, they are attracted together, and that overcomes the electrical repulsion between protons in your atom. But of course, when you break them, you can actually release huge amounts of energy. And of course, there's
sorry,
these things
Steve.
called...
Sorry to interrupt. Yeah, camera still off.
Is it?
Yeah.
Gee. Is it on now?
Yes, thanks.
Doesn't come on my screen for some reason. I don't know why.
It's all good now.
It's strange. I don't see it on my screen either. I'm blank on my screen. Anyway, well, let's press on. So I think what's happened, and please forgive me, everyone. We're trying to run teams with programs and slides and try and talk and present at the same time. It's obviously a little bit challenging, but it's worth doing, I can promise you now. So we've got neutrons, protons, sigmas, and obviously mesons and leptons associated with electrons, neutrons, and muons. So these are obviously the underlying bits of matter. Obviously, there's fundamental particles, and obviously we have the following forces, which are strong nuclear force, electromagnetic interaction, and the weak force and gravity. So you've got basically these forces. And oddly enough, over the last 20, 30 years, since when I did physics 40, 50 years ago, that really ages me, we still have those forces as a critical thing. And just bear in mind, obviously, the electromagnetic forces are considerably stronger than gravity. So quite important to pick that up. And then, of course, we've got photon interactions and gravity are well understood, but of course, we can't tie those theories together at this stage. So there's obviously a lot of uncertainty there. It would be lovely to get a comprehensive, as I say, unified theory of everything, but that's not happening at the moment. But we will come to that in a tick. So really, the next little discussion I want to talk about is how does physics relate to the other fields of science? So in other words, our friend here, Mr. Professor Richard Feynman, said, what is the relationship to other fields? And it's quite interesting, some of the comments he makes about the other fields. So mathematics and physics is a pretty tight relationship, as you would expect. Mathematics is a pretty tight key part of physics. The other interesting area is physics and chemistry. And obviously, physics is very much related to that. Statistical analysis, where you actually tie physics and chemistry together, statistical analysis. So again, statistics plays a really key part here. You may say chemistry also plays a key part in biology, inorganic chemistry, organic chemistry, molecular biology, or critical underlying parts. Biology and physics play a very key role, and obviously the mystery of life. No one knows really what life is about and consciousness and stuff like that, but physics is right at the bottom of all that. Krebs cycle and biochemical engineering, biochemical energy, life in biology is a pretty critical part, and physics and is a key underlying part. Even with proteins and DNA, physics is deep down in the bottom there, DNA and genetic information. And of course, another area where physics comes very, very close is obviously astronomy and physics, analysis of stars and stuff like that. Physics is a pretty critical part. And of course, with geology, geophysics is a pretty critical part. Just analyzing structures, rock structures, using electromagnetic waves, ground penetrating radar, geology is a pretty critical part. So of physics plays a really key part. A little esoteric, and I'm surprised that he mentions this, but he also suggests that psychology and physics also has a little tie-up. And obviously that's to do with consciousness as well. So there's always some connections between the two. So physics is a key building block of all the sciences. Now let's just talk about physics and conservation of energy. And obviously you would have all gone through all the theories with conservation of energy. And obviously it's a pretty critical building block. And one of the biggest areas of physics which played a big role in disproving was obviously perpetual motion. And I suppose from a business point of view, you can summarize it very clearly by saying there's no such thing as a free lunch. So basically, perpetual motion was also a area where physics debunked. Reversible machines, conservation energy, and obviously gravitational potential energy and work. And I've got a nice little program to demonstrate the conservation of energy. Some nice little demo, which I'm going to go on to now. And obviously, you've got different types of energy, gravitational potential, height, kinetic energy, half mv squared. Bearing in mind that I'm using Newtonian physics. I haven't dared mention the Einstein adjustments, elastic energy. One of the most important theories, formulas is force equals minus kx, Hooke's law, which is when you have a spring, and obviously other energy forms such as mechanical or electrical, chemical, nuclear, mass energy, and stuff like that. So, and obviously with conservation of energy, probably one of the most famous examples. I'm just going to quickly share. Sorry, Barry, if you can just bear in mind which slide that's on. I'm just going to jump onto conservation. Let me just go on to that. Conservation of energy conservation. Let me just go into that. And the best example of energy conservation, which I always love demonstrating, is, of course, the mass spring. There we go. Okay, can everyone see that? Barry, can you still see that?
Yes.
Okay, energy conservation spring mass system. Oh, my pictures come back, which is good. Okay, so here we've got energy. So you've got a spring with a mass and it's bouncing up and down. And it's always interesting to see the interchange here. And again, these programs are freely available. You can set them up and run them on your machines. You can do all sorts of things. So here we have got an example here of the interchange between kinetic and potential energy and the total energy. So you can see the blue is the kinetic energy and the potential energy is green. And of course, as your spring extends like that, it stops and then it gradually moves back again. So you're getting that movement up and down. And of course, this is a beautiful little program to show how it operates and how your total energy stays the same. As you can see at the top there, dotted dash line, but the actual kinetic and potential are constantly changing. So it's quite an interesting little demonstration that. And again, as I said, you can easily run this program and do all sorts of manipulations on it. And in fact, in the program, you'll see, you'll see the kinetic energy and the potential energy 0.5 times K times X squared. So obviously a very simple program, but gives you a quick demonstration. Okay, let's go back to stop sharing, go back to the screen again. Bang, 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 bang. If I can go back, great. Let's go back that slide. Barry, can you bang that slide back again?
Yes.
Sorry about that. Great, thanks very much. Excellent. Okay, so we've got conservation energy, and now we're talking about quantum mechanics. Let me just get on to that. Quantum mechanics, and we'll come to the quantum mechanic issues shortly. Obviously, energy transformation, heat energy, mass energy, conservation, and thermodynamics. Here's an interesting comment here. Thermodynamics and entropy, particle conservation, these are all conservation laws in physics, so they're pretty important. But the one here, which I think is just worth spending a few moments on, is talking about this wonderful concept of entropy. Can anyone tell me what entropy is? Just chat in the box there. What is entropy? Oh, yeah, okay. Adrian's made a really good point there. Sorry, Adrian, thank you very much. Kinetic plus potential plus loss. You're absolutely right. There's heat loss, there's loss, and thank you very much. So otherwise it'll be perpetual energy. Thanks, Adrian, Mr. Adrian de la Cruz. Thank you very much. You're absolutely very good. I always love people picking me up and telling me, sorry, Steve, major mistake there, matey. Anyway, can you tell me what entropy is? Just type in the box, entropy. Because energy conserved may become unavailable due to entropy. It's something which I was puzzling about the other day, and it's actually really quite interesting to talk about. Decay, yeah, entropy can be described as decay. Thanks, Mr. Mark Skelton. Thank you very much. State of disorder. Yep. So it's really disorder, but anyone disorderly, absolutely right. So entropy, as the universe ages, entropy increases, and you only go one way. You have the arrow of entropy, which I think actually ultimately is time, although I'll have a physicist pull me up on that. But the interesting comment there is energy conserved may become unavailable due to entropy. Really interesting comment. So basically what's happening, what they're saying there is that, well, what Mr. Professor Richard Feynman's saying, he's saying, look, you've got a container with heat in it, and it's got heat available, it's doing things, but if you let that heat go out into the universe, spread out, the entropy is increasing, but that heat is now unavailable. It's not in one spot anymore, it's spread out. So the entropy's gone up, but that energy is still there, but it's spread out so vastly that you can't use it anymore. So it is a particular thing. Yeah, rate of disorder. Thank you very much, everyone here. Entropy is a really critical part of thermodynamics and obviously the universe. And as I said, very closely connected to time, I believe. Anyway, thank you for that. So thanks very much for your contribution there, everyone. You're absolutely amazing. Thank you very, very much for being so proactive and positive. I am learning more from you than you'll ever learn from me. So what we're going to talk about now is obviously energy sources and law of gravitation. And obviously, there's a whole lot of very interesting laws there. And probably one of the most famous astronomers was Kepler. And he came up with these laws where planets move. I never really realized it, but when you look at the planets moving around the sun, well, we always used to think they all move around the Earth, but of course that's not the case. They move around the sun, but they do it in an elliptical orbit. And there's some really interesting, the second and third law, always worth bearing in mind. The third law is particularly interesting. The square of the period is the time it takes to go right round, is proportional to the cube of the orbit's radius. In other words, you take the radius, multiply r times r times r, and the actual period, the time it takes, is proportional to that. I mean, for someone to pick that up in the 1800s is simply amazing. Then you got Newton's law of gravitation. And by the way, I mentioned to you earlier on, I said, I created all these slides in a few hours. And you say, yeah, okay. But can you see this particular one here, this graphic here? It is complete gibberish, absolute gibberish. I mean, it looks very, say, very interesting and useful, but it's actually, it's not, it's the mind of a madman, and it's not my mind, I can assure you. Anyway, it looks quite good, I suppose, but it's not, doesn't make much sense. So obviously, Newton's law of gravitation, again, is really fascinating. And I want to just talk about that in a moment. And obviously, the moon falls towards the Earth, and you have obviously 16 feet. I apologize for my non-American friends here. We use 16 feet. The is obviously not quite correct. Let's just make sure we all understand the gravitational speed. The acceleration is g equals 9.8 meters per second squared. And if you have an object falling, can I ask anyone in the box to tell me how long it will fall in 1 second? 1 second. Thanks, Austin, for those encouraging murmurings, words. How much will your ball fall in 1 second? Yeah, it'll fall. No, unfortunately not. It's not a direct linear relationship. Otherwise, that would be correct. Unfortunately, it's a non-linear relationship. It's a square involved. So it's basically 4.5 meters, 4.4 meters, 4.5 meters or whatever. So you don't fall. And in fact, you can work it out. 16 feet divided by 3 is about 4.5. Yeah, half of 9.8. Yeah, thank you very much, Mr. Onoda. Absolutely right. Got me fooled initially when I thought about it. I thought, oh, well, it's 9.8 meters per second, but it's not a linear relationship. Always a bit confusing. And of course, you have obviously universal gravitation and tides, which of course the moon does cause some interesting issues. It's a beautiful world, but it causes a bulge, a water bulge, which is always a bit daunting to know because of the moon attraction. And obviously, one of the other little demonstrations I'd like to run is the escape velocity. And obviously, gravitational and double star systems. You see these gravitational perturbations, and then they say there must be something else hidden there which we can't see. That planet is moving in a very strange way. And probably one of the most interesting areas which no one knows the answer to is, of course, dark energy. What is it? Dark matter. It's hidden out there because there's some very strange things happening in the universe with gravitation, which we can't predict. We can't say why they're there. And the theory is that there's some dark matter which we can't see. But anyway, that'll be another topic for another day. So very interesting on a gravitation on a cosmic scale. I don't think I mentioned dark matter there, but I should do. And of course, we have this wonderful theory of gravity and the formula between gravitational attraction. And probably one of the really interesting things is the gravitation and electrical forces. Gravitational force is very, very, very tiny compared to electrical forces, so really important. Now, gravitation and quantum mechanics is a big challenge because, of course, we can't reconcile the two. And gravitation, of course, we're always thinking there is a particle out there which is called a graviton, but of course, no one's identified it. But interestingly enough, and it's really fascinating to observe this, there's some really good data of gravitational waves sweeping through the Earth and being measured. I mean, it's unbelievable. You can actually see the measurement of the gravitational wave going through. And it's also important to realize that gravitation takes the speed of light to be transmitted. It doesn't just happen instantaneously, it takes time to progress through. So it's like the speed of light again. Nothing's faster than the speed of light. Gravity is not instantaneous, it takes a finite speed. So the really important observations there. But we still can't tie quantum behavior and gravity yet. So I've got another little demonstration here. I just want to run quickly, if you can forgive me for a moment. I'm just going to get it working. Orbital mechanics, which is quite an interesting little demonstration. And it's a wonderful discussion that we always have on different launch speeds affecting an object's trajectory around a central mass. And it's quite an interesting little demo. I'm just going to run it quickly. Sorry to jump in again there, Barry, with another pest of a change of slides. I'm just going to quickly run it. Orbital mechanics. So here we are, orbital mechanics and gravity. Now, of course, one of the biggest dramas we always have is you have a rocket blasting off on the Earth and the interaction. And this little Python program gives a beautiful little simulation of escape velocities. I thought it was beautiful. So it's got the whole, you'll see the equation in the middle there, the acceleration and stuff. And let me just run it. And of course, here you can see orbital paths at different launch speeds. So again, you've got the central mass, that little yellow thing in the middle there. You should see it. Can you see that, Barry, or is it a big blank blotch?
Yes, we can see it.
Excellent. Thanks so much. So you've got the little central mass, and then on the right-hand side there, at about 5 units, you'll see 5 units with my cursor. You'll see these animals, rockets shooting off, and you'll see the first one is actually V naught equals 0.5. You can see it sort of shoots off from Earth here and it goes around the moon, but it's tied. It's just tied to that object, so it just keeps circling around in orbit. So as you increase your speed up to V naught equals 2 units, 2 units of speed, you can see it blasts off the red one and it escapes. Boom, it's gone. So it shows you the actual gravitation attraction is really important, and it actually does cause a lot of angst when you're trying to fire a rocket off because it gets sucked in and pulled in. So it's always a bit of an issue. So it's a beautiful little program to show that. And again, as I said, I'll make these programs available. It's a nice little demonstration, and you can change it and do all sorts of little things using Newton's law of universal gravitation, which is G equals m1, m2 divided by r squared. And r squared is always interesting, sitting there, and it's basically relating to the area of a sphere, 4 pi r squared. But let's go back. Let's go back to the back to our session again. There we go. Let me just go back again. Sorry, I'm just going to jump back in again. Sorry, stop sharing. Okay, thanks, Barry. Thank you very much. Thanks for taking control. I'm sorry we're always running out of time. So the next thing we want to talk about is quantum behavior. So let me just take control. Thanks, Barry. 5 minutes left. I know time is always tight. I'm always pushed. Sorry about that. How do we... Can we go directly to it, Barry? No, maybe not. Yeah. No, that's all now. Okay, thanks very much, Barry. You changing the slides for me, are you? Great, quantum behavior. Okay, so really, the final little discussion here, and I'm sorry to take so long to get to this point, but basically the problem that we've got is quantum behavior. And that's probably the thing which confounds all this wonderful classical physics that we've been talking about. And that is that there is uncertainty. And as I said, Einstein plaintively said, he said, hey, God doesn't play dice with the universe, but in fact, God does, she does. So, it is a little bit daunting when you think about it, because quantum behavior is not logical. It's very illogical. And there's a very good little demonstration here, which I'll run at the moment. But basically, we can assume that light waves consist of little packets of energy, photons. And there's this wonderful um, experiment called the double slit experiment, where they fire you have waves going through it, and the waves that go through the double slit actually tend to interact with each other. So you have a really interesting quantum behavior, which I'll demonstrate there. And basically it's saying that everything in the micro world, atomic world, is characterized by probability. And there's a wonderful thing in quantum mechanics called the wave function. But basically, we model everything as a wave. And this whole process of saying an electron is in a particular point is not the case. And there's an uncertainty associated with predicting everything. And people have tried the most amazing thought experiments to try and say, hey, I can predict by I can identify where a electron is. The problem is you can't identify the precise location of electron and its momentum with precision. You can only get it up to a certain level of precision. It's a probability function. So it's smeared out. And that causes a lot of issues in life and trying to predict things. So this is where we have a really interesting situation with, as I said, with the slit, which I'm going to run a little demonstration on with a thing. And the idea is that you have a slit, two slits, and you're firing electrons through them. And electron you would assume to be a individual particle, a tiny particle. And the thing is, when they fire them through the two slits, the electron will only go through one of two slits. So you've got two slits, bang, here you go. Let me just draw it for you. There's one slit and there's another slit. So you've got electrons coming from here and you fire them through the slits. The issue that happens is that the electron creates a interference pattern behind it. And you say, well, that's fine. And I'll demonstrate that in a moment. And you will say, well, that's fine. They can create an interference pattern behind it because one electron goes through one slit, one goes through the other slit. But the actual fascinating thing is that the electron actually, it tends to almost appear to actually be a wave because it interferes with itself on the other side. So as it goes through, it actually goes through one of the two slits. You can't predict which one. And that does cause a bit of chaos in terms of trying to predict the electron's behavior. And the idea is that as soon as you fire a photon at an electron to say, I want to understand where that electron is, you actually change its position. So you cannot get away from the fact of that we always think of reality as fixed and normal and everything's in one place. But the actual thing about quantum mechanics is that the process of observing impacts on the observation, which is horrific because it's reality. It shouldn't be. So that is a really interesting concept, which causes lots of issues and angst. So the idea is that you have a little demonstration, which I'm going to run now. The measurement actually changes the system. So that's probably one of the most important concepts with quantum mechanics. And that is the building block of everything we do. The problem that we've got is that we can't reconcile quantum mechanics with the other classical areas of physics very easily. For example, like that. So that is a really interesting conundrum. So I'm going to run this last demonstration here, and it's called Heisenberg's uncertainty principle, which says that you can't predict exactly the position and the momentum of an electron or any subatomic particle. It is a probabilistic, I think it's 80% chance it's over here. So, which is always a bit distressing. So let's have a look at this little demonstration. I've got the last little demonstration. Yeah, so these are some of the concepts of quantum behavior. As I said, nothing is position and momentum. There's a fundamental limit, which is the issue. So I just want to run that demonstration. Barry, this is just the last thing. I know I overshot on time. I just want to quickly do this last little demonstration. Sorry, let me just get the demonstration going. Quantum double slit experiment. Let's go on to that. Okay, oops. Okay. Share this window. Sorry, let me just get onto that. Sorry, I'm just going to get onto that. Share. Here we go. Quantum double slit. There we go. Okay, everyone, can you all see that? Barry, can you see quantum double slit experiment simulation?
Yes, Cliff.
Okay, good. Okay, so this is the last little demonstration I just want to run through. So basically, we've got a double slit and we've got interference patterns. So this shows you the sort of two particles traveling through two slits. So they have a detection screen histogram, and you have it building up behind here. So the point we're trying to make here is that you have a random approach with the particles traveling through the screen. So on the left here, you'll see the electrons being fired through the screen. And of course, there's a bit of a pattern forming here. So false quantum behavior. So we can say false equals quantum behavior interference and true classical behavior. So let's have a look at that. Observer on equals false. Observer on equals false. So that's when we observe the particles. When you don't observe the particles, let's change that to false. Sorry about this, guys. I'm just going to quickly run through this demo. Again, this is a quantum demo now. And of course, you can see here, this is quantum. We're not observing it. This is purely a interference pattern forming. As soon as you observe them, the particles immediately behave. They go into, you can actually track them and go, there's no observation, there's no interference pattern. As soon as you have quantum behavior, which is classic quantum behavior is false, over there, false, we actually have, we're not observing electrons, we're not firing a photon to try and find out where they are, you get an interference pattern. So basically the electron actually splits, and if you fire one electron, it'll split between the two and create an interference pattern. Obviously you need lots of them, but the point is that quantum behavior, when you observe it, you change what you're observing. So the observation, what's happening out there, depends on the process of observing, which is a very difficult concept to get to grips with. Anyway, let's go back. Sorry, let me just kill this. Stop sharing. Bingo. Okay, Barry, if we can just go back to the slides and close it off. Sorry to go on like this. Thanks, Barry. Thanks for putting up with my jumping around the screen. Everyone must say, what on earth is going on? Okay, let's go on. Okay. So, right. Okay, so as I said, we've got to the end of the presentation. I'm sorry to overshoot my welcome, but basically the idea is that we've spoken about classical physics for most of the presentation, but unfortunately the disturbing issue is that we've got quantum behavior where the process of observing disturbs the reality, and that's a very, very difficult concept to get to grips with. But it's all part of the process of getting. So let me just close off by saying thank you very, very much for joining in. I've taken this book and I put it on the slides. Hopefully, Barry, can you see me? I can't see myself on my.
Yes, we
Can
can
you
see
see?
it, Steph.
You
Yeah.
can see. So this book here is basically encapsulated, obviously, without getting sued for copyright infringement, but it's in the slides. And I must say a huge thank you to Professor Richard Feynman for giving me some idea of his thoughts, because it is really interesting. And thank you very much for sharing my passion for physics over the last hour. I really appreciate it. And I just want to obviously thank Barry, Britta, for allowing me to present to you wonderful people. A few thousand people contacted us, but to listen in. But thank you very, very much. Over to you, Barry. Thank you very much.
Thanks, Steve, and thanks for everyone for sticking around. I see some comments, and I hope you've learned a lot. And yeah, so just some of courses that have been covered in this topic. So we've got mechanical, electrical, industrial automation, and civil. As I've mentioned, feel free to reach out to our website, and you'll have all these information. Some of the upcoming courses, if you have any course that you are looking at, you can just go on our website and familiarize yourself with the course schedule, and then you can see what coming next. And then for those who have been asking about the certificate of attendance, if you can just scan the QR code there, you should be able to complete the form. Alternatively, I will share the link with you, and then you can just click on that link, complete the form in order to claim your certificate of attendance. Just know that you've got up until Monday the 28th, so just do that as soon as you can. Thanks.
Thank you very much, Barry. I think that's all, and thanks, Britta. And thank you very much, one and all, for attending. And thanks, Barry, for jumping around so vigorously. I'm sorry to hammer you so much with the slides. It must be an easy way of doing it, but thank everyone for
Yeah.
participating. I really appreciate it. But it was a bit jumpy, but hopefully everyone saw, and hopefully, funny thing is I can't see my picture, can't see any videos on the screen now. So obviously Microsoft Teams has crashed somehow. But
Probably, yeah. Thanks, Steve.
but thanks so much,
All right,
Barry, and
thanks.
thank you, Britta. I hope you have a good afternoon. Thank you very much.
Cheers. Have a good one.
Cheers. Yeah. Thanks,
Thanks,
everyone.
Steve.
Bye.
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 Thanks, Britta. Thank you so much. Bye. Bye.